Okay, in 15.7, we're going to be taking a look at something called surface integrals. That's essentially the two-dimensional, or if you will, three-dimensional, depending on whether you're looking at the input or the output, analog of a line integral. So with a line integral, remember what we said is we had a one-dimensional curve, but that curve was living in either 2-space or 3-space. I've written it here so that this would be a curve in 2-space, so that every point on that curve has an x and a y value. Now that means that if I have a function of two variables, I could assign a z value, or a height, to every point on that curve. And essentially we saw what that did is that created a little ribbon of, a two-dimensional ribbon of signed area. And we said that this line integral would be the signed area of that little ribbon. Okay. Here, this S is corresponding to arc length. So it's like we're multiplying little sections of curve, their arc length, which is the base of our region, times this height that we're getting. Okay. Of course, if my curve is in 3-space, my function will be a function of 3 variables. That would mean that the height would actually be a w value in the 4th dimension. Becomes a little bit harder to visualize what's going on then, because then my ribbon of area would be a 2-dimensional surface living in 4-dimensional space. You might say, well, that's just so wacky, why do we do that? And the reason is that it's usually not actually a geometry problem. Almost always the signed area that we're calculating is a metaphor for some other quantity. So that, for example, if this function were the mass of a very thin wire that we were treating as an idealized one-dimensional object, sorry, not the mass, if this were the density function for that thing, then when I integrate density with respect to arc length, I would be calculating the mass of that wire. Another classic example is if my integrand here happens to be the dot product of a force field with a unit tangent vector, then I know that what I'm calculating is work. Okay, so we've got the same basic idea here. If I have a surface, and our textbook calls this S, I'm not crazy about that because they're using the same symbol, capital S here, that they're using here. This capital S means that we're integrating with respect to surface area. That's different from this lowercase s, which was arc length. Okay, so little s is arc length, big S is surface area. I'm really not crazy about saying I'm going to integrate with respect to capital S and then naming the surface capital S. However, that's what the textbook does. So I'm going to respect that and do that just so it doesn't look any weirder than it has to when you're doing the homework. I think that's a poor choice. I think since we're free to call our surface whatever we want, oh my goodness. I apologize. That should have been a double integral sign there. I'm very sorry. I left out an integral sign. This is absolutely a double integral over a two-dimensional object. So the basic idea is that S, whether it's poorly named or not, is this two-dimensional surface, but it's living in a three-dimensional world. So every point on that surface has an x, y, and z value. Okay. So if I have a function of 3 variables, I could assign a w value, which I can think of as a height. I'm attaching a height to every point on this two-dimensional surface. Now, it's a little tricky to visualize because since my two-dimensional surface is living in a three-dimensional world, I'm already using x, y, and z just to describe the points on that two-dimensional surface. So this height would be a w value in the 4th dimension. So essentially what I'm creating is a three-dimensional solid that lives in a 4-dimensional world, and then I'm going to try to calculate the signed volume of that. That feels crazy until you recognize that we're not really doing a geometry problem. That signed volume is going to be a metaphor for something else, just like the signed area that we get here is a metaphor for something else, depending, of course, on what the integrand actually means. So we'll talk a little bit about what this means and see some examples of applications. Right now, I just want to focus on how we would calculate this signed volume of attaching a height to every point on this two-dimensional surface that happens to live in 3 space. Now, when you first look at this, you might have the same reaction that you had when you first saw a line integral, and that might have been to cry or to throw a tantrum or to just put your head down on the table and despair, because it looks really weird. We're doing a double integral, but we're integrating a function of 3 variables, and we're integrating with respect to surface area, and that doesn't match any of those 3 variables. But hopefully, you're a little less prone to despair than you might have been when you first saw a line integral, because we had a perfectly good way around that, and that was to use parameterization. Okay. And I cannot emphasize this enough. The power of parameterizations is that it matches the number of variables to the dimension of the object rather than to the dimension of the space in which it lives. So when I have a one-dimensional curve, whether it lives in 2 space or 3 space, I can describe it with 1 variable. When I have a 2-dimensional surface, even if it's living in 3 space, I can describe it in terms of 2 parameters. The reason that's so important is if we're setting up an integral, if I'm integrating over a 1-dimensional object, it's going to be a single integral. If I'm integrating over a 2-dimensional object, it's going to be a double integral. But each time I integrate, I get rid of 1 variable. Because each time I integrate, I plug in the limits of integration for that variable. So if I start with 2 variables, and I integrate, the first time I integrate, I'm down to 1 variable. The second time I integrate, I'm down to no variables. I've got just a number. Okay. So that's what we're going to do. We're going to use parameterizations in order to evaluate this. Okay, so let's do this. So let's suppose that in the UV plane, I have some beautiful region D. Might or might not be a rectangle, doesn't matter. It's a lovely region. Okay. I'm going to have my parameterization R of UV that's going to map that to some surface, potentially curved surface, in 3 space that we're going to just call S. Okay. And what we're going to do is go through our usual 4-step process: chop, approximate, add, take a limit. Okay. I'm actually going to write out the Riemann sum that we get both in 3 space and in 2 space. Okay. So, step 1, we chop. Now we always chop the domain of our region into little pieces, and although it's not strictly necessary, it's certainly strategic to chop it into equal length pieces, equal size pieces. So I'm going to have just a bunch of little rectangles here where the base is delta U and the height is delta V. And that way, delta A would just be delta U, delta V, and that's the same for all of them. Okay. That, of course, is going to induce a chopping of S into little patches of surface. Okay. Like so. Okay. And so I can work with each of those little pieces. Now, these all have the same area. These don't necessarily, because it's entirely possible that this parameterization stretches this into something that has more area or compresses it into something that has less area. And it's entirely possible that it stretches this part and compresses this part, and it stretches this part but a little less than it stretches that part. Okay? So these pieces have a constant area, these pieces do not necessarily. Okay, once I've chopped things up into little pieces, I want to approximate. So I'm approximating the signed volume that I get by attaching a signed height, a signed W value, to every point on each of these little patches of surface. Okay. So what I'm going to do is I'm going to suppose that I have some point here. I'm going to just call this point Pij star. Okay. So Pij star is a representative point in the ijth rectangle, and that's in the UV system. So that would be Uij star, Vij star. Okay. Now, let's suppose that that maps to a point here. Okay. I'm going to call that Qij star. Okay. So, Qij star, let's write this down over here. That's going to be a point in 3 space. It's the image of Pij star under this transformation, and it would have a representative x value, a representative y value, and a representative z value. But the connection between them is that R, my parameterization, maps Pij star to Qij star. Okay. So that's going to be my representative point. So if I am approximating things, I can say that what we're doing is we're looking at f of Qij star, working over here. I would basically go into denial. Okay, so the height that I'm attaching over this region may not be the same for all of the points, but a changing height makes my computations more complicated, so I go into denial and I pretend that the height is constant at whatever value it is here. And then I would multiply that by the area of the base. Okay. Now here I do need to have these subscripts because, as I said, the area of this ijth piece might not be the same as the area of a different piece. Over in the UV system, I rigged it so that the areas of each rectangle were the same. Can't assume that the areas of each patch are the same. Okay. So this is how I would approximate my signed volume, expressing it in terms of x, y, and z. Okay. So this would just be a representative height multiplied by the area of the base. But I know how to approximate that area of the base. So if I express everything in terms of my parameters, it would be f of r of Pij star. That's the same representative height, but I would then approximate that surface area. And I would approximate that with the magnitude of del r del u crossed with del r del v, evaluated at that same representative point, Pij star, times delta u, delta v. This is what we saw in section 16.6, was how we approximated the area of a little patch of this surface living in 3 space. So here I've just got my representative height expressed in terms of u and v, and then an approximation of that area. Okay. All right, so I know where I want to go with this is I want to just finish my 4 steps. I want to add and take a limit. I'm a little concerned about this video running over in length, so I'm going to stop this video here and we'll write up the last 2 steps when we pick up in the next video.